All right, in this video, we'll look at theorem 1.4.3 and we'll prove it. So assume that the functions f1, f2, fn have continuous n minus first derivatives on R. If w of x is not 0, so w of x is this determinant here, this Wronskian. If that determinant is not 0 as a function, is not equal to 0 as functions, then this set is linearly independent in f of r. All right, so it's a very computational way of proving that a set of function is linearly independent. And so we like it. All right, more precisely, as soon as there is one x in R so that the determinant is not 0, the set is linearly independent. If the Wronskian is equal to 0 for every x, then we cannot conclude anything. All right, so let's prove this. We're going to prove the contrapositive. So we're going to flip it. Instead of assuming this and proving that, we're going to assume that this is false. So we're going to assume that the functions are dependent, and we will show that when that's the case, then this is also false. Then w of x is 0. Right? So it's a logically equivalent statement. So I'm going to assume that a1 f1 plus a2 f2 plus an fn is equal to 0 as a function, and that a1 an are not all zeros. And so then I have the same equation if I differentiate it for the first derivative. I have the same equation for the second, and I have the same equation for any derivative. Sorry, wrong notation. N minus 1 underneath and n minus 1 as a derivative. Yeah. A n f n n minus 1 equals 0. All right, so if the functions are linearly independent, then all of the derivatives are also linearly dependent in exactly the same way with the same coefficients. That means that if I take any x, I have that a1 times the vector. So now if I plug in x, I get real numbers. And so this is a real vector. So, sorry, f1 n minus 1 of x. And then a2 times the same idea, but with f2. And so on. Oh, took way too much room for this. I'll give you more room. Let me shrink this so you can still see what I'm doing. All right, so the vectors are linearly dependent vectors. F1 of x, blah, 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 F2 of x, blah, 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 and so on. And so that means if you go back, this is in Rn, if you go back to what we did in the takeaway, I think, yeah, takeaway here, if the vectors are linearly independent, then determinant of A is not 0 and the other way around. So if determinant of A in this case is computed, since I have dependent vectors, the determinant of this matrix will be 0. And so the Wronskian will be 0 too. All right, so let's use this theorem in an example. We'll do that in the next video.